It's recording. Thanks, team. All right, so 6I. The whole topic relies on you understanding what we call a unit circle. Everything comes back to this picture. The better you understand this picture and what is actually happening to the circle, the better you understand the topic. Yeah? So unit circle, what it means is if you had a unit length as your radius, okay, unit. So it doesn't have to be 1 centimeter or 1 millimeter. It could be 1 meter. It doesn't matter. The point is this is a width of 1 unit length. Now, if this radius is a unit length of 1, there's a couple things we can then extrapolate based on our previous understanding. We understand that if I know the radius, I can also find the distance around the circle. Now, the distance around the circle is called the circumference. Now, to find the circumference, we know it is pi times diameter or 2 pi r. So 2 times pi times the radius, fill that in. But if the radius is 1, okay, if the radius is 1, then the circumference must then be what? 2 pi. 2 pi, because r is 1. So in a unit circle, doesn't matter any circle. The point is the theory is saying if you had a circle and it had a radius of 1 unit, then what would the circumference be of this perfect circle? We know that then the circumference is 2 pi. This is going to lead into the understanding about radians on your calculator versus degrees. Okay, so here, what we can then conclude is that in a circle, the distance around the circle we now know means that the measurement, this is the distance, right? Going all the way around is an exact 2 pi distance. Now that could be centimeters, 2 pi centimeters, 2 pi meters, 2 pi kilometers, doesn't matter, right? But what we also know is that in a circle, in terms of measurement, in terms of angles, to make one full circle, what is the angle equivalent to? 360. So that means what you can relate to now is then, in order for a distance of 2 pi to occur, you had to rotate, starting at 0, starting at this point as being 0, you had to rotate 360 degrees to make 2 pi distance. Therefore, 360 degrees is equivalent to 2 pi radians because the distance and the angle is actually measured at the same rate. True, as you're moving the radius hand, the distance covers a certain amount and the angle is also covering a certain amount. Does that make sense? Okay. This leads us into 2 formulas that you can derive from. If you understand just that property, you can always derive the formulas. But if you don't get it, you can memorize the formulas yourselves too. Okay, so here, this is how it works. By ratios or just by the logic here, if I wanted to know what 1 degree is equivalent to in terms of distance, meaning if I moved only 1 degrees in that circle, starting here, and I moved 1 degrees anti-clockwise, it must make a certain distance. True? So that distance, well, how much is that? Now we can work that out by looking at this. We're saying, well, 360 equals 2 pi. So to go from 360 back to 1, what do? Very good. To divide 360 on both sides, divide this side by 360, and that gives me 2 pi on 360. But we can simplify that. 2 pi on 360 is simplified to? Oh, yeah.
So 360 degrees equals 2 pi, but shouldn't it be radius? What is the radius? Or is it just for the scenario?
The radius for this scenario, because we're saying a unit circle, meaning unit, if it was just 1 length. So if the radius is 1.
Oh, but is it just for this scenario?
Correct, because this circle with a unit length of 1, you can actually generalize it to any length or any circle. That's why it's generalized that for any size circle, the circumference proportionally, the distance will be 2 pi across all. Yeah, but I get what you're confused about. If the radius increases, that's technically what we call a dilation. We're stretching the radius, yeah? So in this case, we're just saying at a purest level of just 1 unit, what would this circumference be?
I'm still a little confused. If the radius was 3, would it be 2 pi times 3?
Correct. That's good. But then what that means is then you're just doing 2 pi 3 times that amount. Get me? So 3 times that amount is just making it bigger. But the first part is knowing what is 2 pi equivalent to in a unit. Because if you know the first unit, just kind of like how I'm changing it back to 1 degree is 1 unit. If you know 1 unit, you can work out any units. And that's the idea of a unit circle. You start off with the first basic circle, then you can work out any larger circle. Yeah? So going back to this, 1 unit of degrees is equivalent to 2 pi divided by 360, but we can simplify that, and we see that both of them are even numbers. 2 goes in 2 once, and 2 goes in 360 180 times, and this gives you a rule. Is this what you were about to say? Very good. So the rule is, if you want to convert from degrees to what we call radians, the answer is following this rule. Well, what's this rule? You see, if I wanted to ask you, what is 30 degrees in radians? Can you see, if we know 1 degree, so 1 unit, if you know that 1 unit is equal to pi on 180, then having 30 of them just means times this by 30 to get 30 degrees, then I would have to times pi on 180 by 30, because I need 30 of them to make equivalent to 30 degrees. True? What's interesting is 30 times pi on 180, 30 and 180 can be simplified to pi over 6. Very good. This is going to be one of the special angles that you will need to memorize, the radians versus degrees. So here, this is called radians, and I want you to put a note on the side. Radians is actually just the measure of the distance outside of the circle. Because I think that's what students forget or not understand. Radians is the measure of the distance around, whereas degrees is the measure of the angle within a circle. That's the difference between the two. They're not the same. Yeah? We're either measuring the distance around the circle, but it just so happens proportionally the angle and the distance are at the same rate as you're moving. Okay? So this is the formula that you get in the first exercise of the Year 11 Methods course. When they first learn it, they need to learn how to convert from degrees to radians. So this is going from degrees to radians. How do you get it? Times by pi on 180. Or the reverse, if you want to work out the rule for the reverse, it's the same idea. What if I wanted to know 1 distance, 1 unit distance, what would the angle be? So if I wanted to know, if I made an angle distance of 1 radian, so little c represents for radians, 1 unit length and an arc of a circle, what would the angle be? So in this case, same idea. How do I go from 2 pi to 1 unit? You would have to divide by 2 pi. So that means on this side, I divide by 2 pi, and what you get is 360 divided by 2 pi simplified is? Yeah, but simplified? 180 over pi. I just skipped a step there. So 360 over 2 pi, we can see that 360 divided by 2 is 180, so 180 on pi. This is your second formula that usually the Year 11s normally memorize. This is converting radians to degrees. Whereas this is degrees to radians. Yep.
Is this on our? Is this like it's going to be on our test on
Yep.
Monday? Or
No.
is this on our exam?
On your exam.
Okay.
I'm doing it early so that you're going to get at least a weekend and about 2 weeks to revise.
Monday is our individual testing.
Oh my God. Wait, let me pause the video. Here we go. So re-recording, starting from this point, you've got two formulas, and this is just really talking about, well, how do you go from degrees to radians and radians to degrees? I'll explain soon. Once we understand the unit circle, you understand why we need radians and why is it that year 11 level we only use radians and not degrees anymore. Because one of the troubles we found previously when I talked about the number of revolutions, it's hard to figure out where you are in the unit circle if we work in degrees. An example would be if I asked you 5,145 degrees, where on the circle am I? Am I in, especially if I split it up into quadrants, which quadrant would I be in? In degrees, that's a lot harder to figure out because you have to go multiples of 360. But we work in radians because that 2 pi was very special. You see, if I did a little circle on the side here, whoops, I just moved that notes bit, sorry, give me a second. Let's think about why the radians is special. See, if one full revolution is 2 pi, if I did a second revolution, which I'll do a green color now, what would the distance be now if I did 2? 4. If I did now a third revolution, I'll do in purple, what would my distance be now? What's the pattern? It's going up by 2. So all the even pi's are here. Then that means, well, if one full circle is 2 pi, well then, let's think about it for a second. How far is it from here to here? 1 pi. But then that logic, every half circle is 1. So 1 plus 1 is 2, plus another 1, that makes it now 3, plus another 1 makes it 4, plus another 1 makes it 5, but there's a pattern each time you reach this point. 1, 3, 5, what's the pattern? It's odd. All the even pi's are here and all the odd pi's are here. It makes it easier because if I asked you for something like this, what is, where is, well, this might be, actually I'll make it a bit easier. Let's just do 3 pi on 2. Because you can work in halves. So you know that 3 pi on 2 is 1.5. So it's 1, an extra half. Later on, you're going to be learning things like 21 pi on 6. You can kind of roughly guess where 21 pi on 6 roughly is. Because you can work out 4 pi is 24 pi on 6. So that means 4 pi must be here. So you can kind of roughly guess where 21 would be. Can you see what I mean? So working in radians becomes more powerful than degrees. Because if we actually converted this to degrees, using the notes I've just shown you, how do you convert radians to degrees again? What would you have to do? Times it by? Well, not 2 pi. Radians to degrees. What was the formula? Good. This is the radians. Radians to degrees. 180 on pi. So if you got 1 radian, but now I want 22. Was it 22 or 21? 21 pi on 6. If you want 21 pi on 6, I need 21 pi on 6 of these. So then I would times that by 180 on pi. And what you can see is the pi's cancel out. 180 divided by 6 is 30. 30 times 21 gives you what? I know. 630. If I asked you 630 degrees before, I said which quadrant are we in? That's harder to figure out. But with 21 on pi on 6, you guys roughly would have figured out where we were. That's why we work in radians and not degrees. Why do you need to know how to convert? It's because that. So they might give you 630, and then you need to be able to convert it to, or you can just work out the multiples. But that's the reason why you need to first know the conversion. Yeah.
Why is the 1 to the power of C?
No, C is the symbol for radians. Yeah. Don't know. I just know little c is the radians notation. Okay, so the C means radians. So that means 1 radian. Yeah. All right. Is that good? So far, so good? The first bit? Yep.
So wait, so if it's 630, like C, does that mean it's the 630?
No. If it's 630, the little c, okay, this just means that the distance around the circle is 630, whatever the units is. So you see 2 pi c, 2 pi is about what? Double over pi, so 6.2 something, right? The distance, when you say 2 pi radians, what you're saying is the distance around this is about 6.2, wherever it is. Does that make sense? It's just that 6.2 something is too hard to remember, so people say 2 pi instead. Yeah, because one is a recurring decimal, and then writing as 2 pi, that's an exact value, which is easier to speak. It's harder for students to understand. Make sense? But remember, radians is a measure of the distance around the circle, whereas the angle is the actual measurement in degrees. Okay? It's the rotation versus the distance. Cool? All right. So that's the first part for you to understand. Now that you can see the relationship between degrees and radians, we now move into how does SOHCAHTOA come about? All right, so here we go. This is the first bit. Unit circle. Let's look at some basic properties. A unit circle, we always measure the starting point right here. Okay, so it's on the right-hand side. This is where 0 degrees is and 0 radians begin. We always measure, notice the quadrants, when we split it up into 4 pieces, which is like your X and Y axes. Your quadrant goes 1, 2, 3, and then 4. Notice it's anti-clockwise. Okay? This is just by convention. We work in anti-clockwise motion. That's when it's a positive direction. So anti-clockwise is positive, clockwise is minus. So you might want to write that down to help you sort of visualize it. So clockwise is negative. So negative direction versus positive direction is anti-clockwise. Okay, starting point is always right there. This is where unit circle as a theory begins. Here's the theory. When I rotate around the circle, let's say I get to this particular point. So right here. Actually, I'll draw it just on the side so you can see. Imagine I started from 0 and I rotated around the circle up until this point. This coordinate on the Cartesian plane will have a y and an x value, which we say x coordinate, y coordinate. Fair call? But the x coordinate, if you notice, it actually represents, let me do another color. This here is your x coordinate value. True? This is how far x would have to be to have that x coordinate. To have that certain height, this is your y coordinate, right? So that's how you get that point. Now notice as I'm drawing these dots and lines in, notice that you actually make a right-angled triangle. 2, very good. We like to stick with the one that sits on the x-axis, although you could work with the one that sits on the y-axis. We normally start off by teaching unit circle sitting on the x-axis. Okay, the one that Raf just said, that's actually called further symmetry properties, which we then look at y-axis values. Yeah? But let's start. I know. So let's start with just the x-axis. Okay, so just the x-axis. So what's interesting is the angle that I make, which we call theta, created that distance in the circle that I just followed, takes me to this point. So whatever that angle is, that has got me to this point here where it has an x component and a y component. But you see the x component, what type of length is that of the triangle? The adjacent. Because we know the adjacent is, this is not opposite to the angle. This is opposite. Then this must be hypotenuse. But what's interesting, starting from the origin to this point, this is also the, we already know it's the hypotenuse. but it's the radius of a circle. So so hypotenuse equals 1. So radius equals 1. Now this is really special because if I asked you to find that x coordinate, oh yeah, yes, that's right. Because if I asked you to find the x coordinate, so how far is this? That's the same thing as me saying find the adjacent side. But to find the adjacent side, we use cos of the angle equals to adjacent, which is the x value that we want, over the hypotenuse, which is 1. Right, so hypotenuse. So I'm going to rewrite it again. Cos of the angle will equal to adjacent, which is the x coordinate, divided by hypotenuse is 1. But x over 1. So, can you see when I write that xy coordinate can be written as, instead of x and y on that plane, when you type cos of theta, whatever the angle is, you find out the horizontal length, and sine is actually the opposite side, which actually ends up being the height. Okay, that's usually pretty tough for a lot of students to picture. So try to think that for a moment. So x, I want you to write here just to help you remember. X is the cos of theta, and y equals the sine of theta. On the side, write horizontal distance to remind you. And this is the vertical distance from where the point is. Okay, so for every point on that circle, that's why this is called a circular function. Every point on that circle has an x length and a y height for that triangle. No matter where you go. So if you think about that circle, then no matter where I end up, there's always a vertical height and a horizontal length. And that's what your cos theta, sine theta represents every time you type on in a calculator. Yeah.
Does that mean tangent is sine over cosine?
Yes. Yes, it does. See, tan, this is so special. Tan, which I told you previously, was the gradient. But notice tan, which is opposite over adjacent, right? So opposite of adjacent. But opposite is the y value, which is over the x value, which is the same thing as sine theta divided by cos theta. But it also turns out that y over x is your gradient. That's what I taught you previously where I played around with the gradients. I asked you what were the 4 types of gradients. Do you remember? What was it again? Beautiful. You had 4 types of gradients. Positive, negative, 0, and undefined. So undef, 0, negative, positive. I'm going to stop there just so you can visualize what's happening there. Okay, so this whole unit thing all comes back to the circle. You start off at 0. No matter where you turn in the circle, it has an x and a y coordinate. The x represents the horizontal distance of that triangle from the origin, and the y represents how vertical it is. So x is cos, y is sine. All right, questions, Joanne.
So you know how it said cos theta equals x over y, and then you said
Yes.
cos theta x over 1.
Yep.
How is y 1?
No. I said cos theta is adjacent over hypotenuse. Okay, so adjacent is this length. Hypotenuse is actually the radius as well. True? Because you're touching the point of the circle, so that must be the radius. Radius is 1, because we're saying it's a unit length of 1. Yeah, so if hypotenuse is 1, adjacent, A, which is what we're trying to figure out, that's the x length. So it must be x divided by 1, but x divided by 1 is just x. Yes? Andrea?
You can zoom into when you know tan theta equals, because I can't do that. Yep.
This one? Yeah, so tan of theta is opposite of adjacent. Opposite from the triangle we can see is the height. Adjacent is the horizontal length. Y over x, well, y we just figured out was sine theta, and x is cos theta. So technically tan of an angle is equivalent to sine theta divided by cos theta. And previously I proved to you or showed to you that y over x is the gradient. Knowing your 4 types of gradients is what tan represents. Okay, so if you type tan of whatever angle, you can actually figure out the gradient around that circle. Okay, that's what you're doing. Or gradient of the line around the circles. For example, so here's an example. Here we go. If I drew, eyes and ears towards the board, thank you. So if I drew a circle again, but let's say this time I'm working all the way around the circle to this point. Okay, I get to this point. That means from the origin, I've got that hypotenuse. That's the radius. But that means the gradient, when you do tan, you're finding the gradient of that line there. That's what you're doing. Okay, that's what tan means. So when you do tan of anything that's above 90 degrees, it should be negative because the gradient's going to be negative that region. Yeah, so if I use my calculator now and I type tan of, let's say, tan of something bigger than 90 degrees. So let's do 91. And it's in degree mode. Whoops. You get a negative answer. Yeah? And that's why we can see that as soon as you pass that 90-degree line, that's a negative gradient. Yeah? So that's what tan represents. Tan represents the gradient of the line. Positive. And then the gradient in this region is positive as well. And then negative in that region. Tan is negative in that region. Yeah. Which is good. That's what I want to lead you to for 6K. It's that understanding. Very good. All right. Shh. Okay. Let's see how much time we got. Yeah, we got about 9 more minutes. Shh. 9 more minutes just so that I can cover this bit. Because once you get this bit, then we can kind of pause there. Yeah, we can kind of pause there just so you can take a breather and then start practicing some of the questions. And then I'll guide you a bit more. Okay? But I just need you to play around with the unit circle first. So, one of the questions that Olivia just asked me, which is good, I hope that it sort of helps you as well. So I just showed you that when we're in quadrant 2, so this is quadrant 1, what I showed to you just then was that by the time you're in quadrant 2, tan, so I'd use T, actually tan, we know that tan of any angle that's bigger than 90 degrees, because I started 0 here, I rotated more than 90 degrees. We know that anything between 90 and 180 degrees, tan must be negative. True? Okay. So this is negative. But then what would tan be in the third quadrant? Positive, because anything from 180 to 270 degrees, we can see that the gradient of this radius, this line, must be positive. So tan of that angle, anything that's 180 to 270 must be positive. What about tan? So the gradient of the line in quadrant 4. Negative. Very good. Because in quadrant 4, can you see the lines? The different types of lines which I drew before. There are 4 types of lines. You either get positive, negative, 0, or undefined. We can see that tan in this region is negative. But let's take it up a bit of extra now. Okay, so I'm going to teach you something about properties here. Tan, you told me was opposite over adjacent, which was y over x or sine over cos. True? One way to sort of work out tan alternatively as well is by looking at your x and y's. So at this point in quadrant 2, there's a couple of things you can logically think about. Is x positive or negative in this region? Negative. So I'm going to put a negative sign here. So that means cos, x is negative, so cos is negative in this region. But sine is the y value, so what would the y value be? Positive. And we can already see positive divided by negative gives you tan negative. Makes sense too. True? And if you followed to this side, it makes sense why it's positive as well. See, if I picked the coordinate over here and I asked you, just in a logical sense, x coordinate, is it negative or positive? X is negative in this region. Right here, so x is negative. Y, the y value, since it's on the bottom. Yeah, so the y-axis is also negative.
Screw this, I'm working at McDonald's.
So can you see then tan ends up being sine over cos, right? But we can see that it is negative divided by negative, which is why it's positive. Take a pause, have a think. Andrea. Yes, left to right.
Oh my god.
Yep, left to right is down. Left to right is up.
Yeah, and then prime.
Yeah. Yes. Yes. That's exactly it. So this would be sine is negative, but cos is positive. All right, drawing your attention back. Did you get quadrant 4 for tan? Sine must be then negative because over here the y value is negative. But the cos value, x value, can you see the x value is in the positive region on the Cartesian plane? So cos is positive, sine is negative. So therefore, negative divided by positive gives you an overall negative. So 1, you can look at the diagram and figure out the gradient already. Or 2, you can work out from the x and y coordinates of each point in the quadrants. So, there is an acronym that you can learn for this. Notice a couple of things here. So I'm going to draw the circle again. The ASTC. All right.
Oh my god.
The acronym is All Student Teachers Cool. All Student Teachers Cool, right? So, all student teachers cool. And now this, let me explain. I want you to see. Shh, shh, shh. Eyes and ears towards the board. Shh, shh. I'm going to write the functions again. Remember the 3 trigonometric ratios? Remember you had sine, cos, tan. Can you see in this region, we said sine was positive, so I'm going to do a sine, positive, but cos was negative, and tan was also negative. I'll get to that. We get to tan. Why is this section? So you can see again. Sine, cos, tan. That's right. So sine is negative. So here sine is negative. Cos is negative. So negative, negative, and then positive. Over here, correct. If you looked at the sine, cos, and tan again, sine is the y values. So the y values are negative here, and the x values are positive in that region. So that's why we say, well, it's negative for y, positive for x, and then negative for tan. So what does the A stand for? All. That's what it stands for. Sine, cos, tan represents all of them are positive. And we like them positive because we usually work with positive values rather than the negative values. But it's special because only the y values are positive here. Only the gradients are positive here. Only the x values are positive here. And here all x, y, and gradients are positive. Now that's big. Okay, that's a lot to take in so far. How do we feel? ASTC? Yes? All student teachers cool.
So I think it should be awesome, silly, trend.
Awesome, silly, tran, cool. If that, whatever makes you remember ASTC. All right. Okay. Oh, awesome, silly, tran club. That's pretty cool. All right, let's finish it off. I'm only going to stop here, so I'm going to finish up to this bit, and then I'll continue later on, yeah? All right, this bit. Let's now try to understand, every time you type these in your calculator, what do they represent, and how do I know all these values later on? I want you to think about the unit circle. Okay, this is what I want you to get to. So where Raf got to, that's what I want you to get to. Think about the unit circle. You are rotating, starting from here. I'm going 180 degrees. So starting from here, 180 brings me to this spot, that exact spot there. So this is where I'm at. So that's 180 degrees. So the question is, at this point, you have an X and a Y coordinate. So when you say sine, which is it representing, the X or the Y? No, X is cos. Y. So, Y value. Listening. So this bit here, we know that this point, remember, it's a unit circle. So that means 1 across this point over here must be 1, 0. But then if you float it all the way here, that's a unit length of 1 as well. So this must be -1, 0. So when I ask you, what is sine of 180? I'm asking, what is the Y value at that particular point? We can see that the Y value must be 0. Or you can think about the height. See, at that point, the horizontal line, that has no height. There's no triangle. Yeah, so that must be sine of 180 without doing your calculator. We know it's 0. But remember, it's not 0 degrees. It's 0, the Y value. The coordinate is 0. No, radians is the measure of distance. Yes. Tan is the gradient. Yeah. Yeah. Sorry? Wait, I can't hear. Team. Year 9s. Sorry, Andrea? Yeah, the rotation. Yeah. All right. Just one extra thing to confirm for your understanding here. If you type sine, instead of 180 degrees, remember 180 is the angle inside. Radians is the measure of the distance, right? But you told me the distance before. What's the distance of half a circle? No, full is 2 pi. It's 1 pi. So instead of sine of 180 degrees, thanks team. Instead of 180 degrees, if you typed in sine of pi, but make sure your mode is in radians and not degrees, then the calculator knows that what you're entering here is not a measurement of the rotation, but the distance around a circle. Sine of pi should be exactly the same as sine of 180 degrees, because one is measuring distance, one is measuring rotation. That's why they're different. Okay, for you guys at the start, I'm sort of teaching you just degree mode, but that's why we use radians, because radians can tell you where you are in the unit circle. Okay? Have a go at filling out these two, because the last end I just used the radian mode. I'm going to give you, let's go with 4 minutes. Answer the next 3. You can discuss with each other, but let's check our answers after the 4 minutes to see if you got it right. Hopefully you got cos of 270 degrees should be 0.
Yes.
0 because 270 degrees is here. That's 0, -1 at that point. Because 1 unit length down, so x is 0, y is -1. So clearly when you say cos, you're asking what's the x coordinate. So it has to be 0. Next one, tan of 270. That's a vertical gradient. So hence undefined. If you did on your calculation, say error. Undefined for 270, and then 2 pi just means that you're moving all the way across to that point. So if you're over here, that's cos is the x value. So at that point, you've got a length of 1, y value 0, so the answer is... Does that make sense? Okay, I'll come around. I'm going to stop the video. There. Next time I'll teach the next bits. Otherwise it gets too confusing. Okay?